Okay, and so we're recording and
We're
the
recording now.
video capture is,
Is on.
okay. Okay, good morning all. Hopefully we're feeling good today. Before we start, I would just like to introduce you all to Dr. Vincenzo Notario, who will be giving you nervous system and muscle and a few other lectures in a stretch, I believe 27th of September. Okay, so he and I basically are doing this course together. So there you go, you know what he looks like. So when it comes to nervous system and on, you'll know who to look for. So today we are continuing on with our lectures on bone, which is a continuation of our connective tissue cartilage lectures from last week. And I'll show you how all three interrelate as we go forward. Okay, so see if I can get this to go forward. Okay. Don't these buttons normally work? Yeah, yeah, okay, thank you. So here are our learning objectives for bone. Know the cellular components and the extracellular components secreted by those cells. So the extracellular material is both organic and inorganic. So know all of those components that make up bone. Know how hormones stimulate bone deposition and reabsorption. Know the architecture and organization of spongy and compact bone. Know the mechanism of bone deposition, calcification and remodeling. And know some of the vitamins and hormones that control bone formation. Okay, and all of these things we will cover. That pretty much covers the entire first lecture. So the things we're going to talk about today after the introduction will be the matrix, the stuff that is secreted by the bone cells, then what are the bone cells that make up bone, and then how the bone is organized. It has specific architectural arrangements. Then we'll talk about how bone is calcified and how the bone is remodeled. It's not a static structure. And then we'll look at some of the factors, nutritional and hormonal, that contribute to the formation and reabsorption of bone. So bone is a specialized connective tissue with a mineralized extracellular matrix. Okay, so what are its roles? I think some of these are kind of self-evident, but we'll just go over them. So obviously it supports body mass. Okay, bones allow us to stand, walk, and facilitate movement through articulating joints, elbows and knees. Protects the vital organs, okay, the skull, thorax, okay, protection against damage of various organs inside. Site of hematopoiesis, where the components of the blood are formed, mostly. And because bone is calcified, it can act as a reservoir of calcium. If the body needs calcium, it can mobilize calcium by degrading small amounts of bone. So we can compare cartilage to bone, so we know all about cartilage from last week. So similarities between cartilage and bone, they're both relatively hard tissues, okay? And they both contain living cells embedded in a matrix. And they both contain, or they both are derived from a common mesenchymal progenitor cell, and we'll go over that a couple of times. So they're the similarities. The differences are bone is vascularized, whereas cartilage is not. You remember that cartilage has no blood vessels to speak of in it, inside of it. And so because bone is vascularized, the cells within the bone have contact with nutrients and can expel metabolic waste products to the vasculature via connections between some of the cells embedded in the bone. And we'll go over that also as well. So you may not think about it this way, but bone is a dynamic tissue. It's undergoing constant change, and that constant change is a function of mechanical stress. So the mere activity of moving around causes mechanical stress. You're pulling muscles against the bone. and there's gravity is pulling against the bone. So that facilitates the remodeling of the bone. So if you're pulling in a certain area where you might need additional bone deposition, the mechanical stress in that area will cause deposition. Bone is somewhat plastic in that it can be modified. For instance, orthodontists, when you have braces put on teeth, the teeth actually move within the sockets of the jaw very slowly, of course, over months and months, but it actually does move. So you get deposition on one side, reabsorption on the other, causing the teeth to move within the jawbone. And you can have loss of bone mass if a person is long-term immobilized. So, for instance, in space flight, you see those videos of the astronauts up there on the space, what do you call that thing? International Space Station, thank you, where they're riding bicycles and lifting weights and doing things like that, because that mechanical stress that they're doing is facilitating maintaining the bone mass. Otherwise they would lose mass. And along that similar line, like people that are permanently immobilized, so somebody that might be in a hospital bed that's brain dead, for instance, okay, they slowly lose bone mass because they're not moving, okay. So when a person is in a hospital for a long time, if they're cognizant, the nurses come in and they get them to do stuff, and they move their legs and they move their arms and get them to do some minimal exercise to try and maintain bone mass. So the remodeling of bone is a function of bone deposition and bone reabsorption, and this is through the piezoelectric effect, where because bone is mineralized and has a crystalline structure, because it's crystalline, when you apply pressure to those crystals, that will generate a small electrical potential. And so if you have a negative potential, that will cause bone deposition. Positive potential, that will generate bone reabsorption. So like on either side of the tooth that's moving in the socket, there'll be a positive and negative side leading to movement of that tooth within the bone socket as a function of the piezoelectric potential generated in the crystals of the calcium phosphate that is the inorganic component of bone. So let's look at the composition of bone. So there's a non-cellular and a cellular component, and the non-cellular component is both organic and inorganic. So first let's look at the non-cellular organic component. Mostly it's type 1 collagen, okay? So you'll recall that the major type of collagen in cartilage is type 2 collagen, right? Except if it's fibrocartilage, then we have type 1, or elastic cartilage, we have elastic fibers. So, but all cartilage has type 2 collagen. Bone is mostly type 1 collagen. In addition to the type 1 collagen, we have our glycosaminoglycans and glycoproteins, the amorphous components of connective tissue. And some of these are specific proteins, and some of them act as calcium binding proteins to facilitate the deposition of the calcium phosphate. And then when this deposition occurs, newly forming bone we call osteoid, which has more organic than inorganic, and eventually it becomes mineralized and becomes fully mature bone. And we'll go over that again. So non-cellular organic, there's non-cellular inorganic, right? And the major inorganic component is calcium phosphate, which when it's crystallized is in the form of hydroxyapatite crystals, and this actually acts as a hydration shell. It can absorb a lot of water in this compound, and that facilitates the movement of free calcium ions from bone, because it can be solubilized in an aqueous environment because the hydroxyapatite crystals are hydrated, and so calcium can be mobilized if required elsewhere in the body. So that's our non-cellular components, organic and inorganic. And then we have cellular components. To look at cellular components, we have to look at bone. A couple of different ways to look at bone. We can decalcify bone by putting it in certain solutions, such as EGTA, EDTA, that will sequester calcium. And when you do so, what's left is the organic component, so you can do things like this with a long bone if you had decalcified it. And then you obviously fix it and prepare it for histology just like you would any other tissue. Or you can actually grind down the bone to a very thin sliver and maintain the bone in the inorganic component, the hydroxyapatite crystals. So you grind it down to extremely thin sliver, and then you mount that on a microscope slide. Has anyone ever done any geology in college, high school? No one's done any geology. Okay, so if you ever did any geology, that's how you look at the minerals, the crystals of rock, same principle. You grind a rock down to a super thin sliver, you slap it on a microscope slide, and under the microscope you can see individual crystals, and then you identify the rock. Same principle. That's how you make, you grind down a very thin sliver of bone, and you can look at it under the microscope. So now let's go back and look at the bone cells that we can identify with these two different methods. So if we look at a schematic of bone, there will be mesenchymal cells, which are basically kind of like fibroblastic-like cells that then can differentiate into our osteoblasts, shown here. And these osteoblasts occur on the periphery of the calcified bone, as shown here. And these osteoblasts secrete the osteoid, which is the newly deposited material. And as they secrete more and more of this osteoid, eventually they become surrounded and trapped within the osteoid, whereupon we call them osteocytes, shown here. And these osteocytes reside in lacunae, or little spaces in the mineralized matrix. So that's the four components of bone: mesenchymal tissue, or pardon me, and then I should say the fourth one is the osteoclast, which reabsorbs bone. So the mesenchymal tissue will differentiate into a blast or a cyte. These can deposit bone. And the osteoclast, which is large and multinucleated because it's formed by fusion of monocytes, so it has a function like monocytes differentiate into macrophages, which are phagocytic, right? So the osteoclast has this reabsorptive role of degrading bone. So there's our four types of cells: mesenchymal cells, the blasts, cytes, and clasts. Okay. So all of these, well, the first two, at least the bone deposition cells, as I said, are derived from mesenchymal progenitors, which can differentiate into an osteoblast on the periphery of the mineralized matrix, depositing the osteoid, and then becoming trapped in that osteoid to become osteocytes, which then are terminally differentiated cells, which means they can no longer change into anything else if it's terminally differentiated. So let's go back and look at each of these different cells in turn. So here's our mesenchymal progenitor cell in this red oval. Okay, and it becomes a committed cell through a number of different factors like bone morphogenetic proteins, and it can either self-renew via various growth factors, platelet-derived growth factor, transforming growth factor beta, or insulin-like growth factor, and it can differentiate into the osteoblasts in the presence of bone morphogenetic proteins and vitamin D3. So there's some of the factors that control the differentiation of the mesenchymal progenitor cells initially into the osteoblasts. And here is our osteoblast now in the red circle. Okay, so now that it's differentiated from a mesenchymal cell into a blast, it can no longer divide, and it occurs on the surface of the newly forming bone, and it deposits this osteoid, shown here with the arrow. Okay, and it's very secretory in activity, and it secretes a lot of factors to promote the deposition of the osteoid. Now these osteoblasts also secrete growth factors that control the activity of the osteoclast. So the activity of the clast is indirectly mediated by the osteoblast, and we'll come back to that. Then the osteocyte becomes terminally differentiated. It was an osteoblast. Now with the deposition of osteoid, the osteoblast became trapped in the matrix, and eventually you see it more in the mature bone, where now it resides in a lacunae. Does anyone speak Italian? I bet Dr. Notario does. No? Or Latin? Anyone speak Latin? No Latin, no Italian. Okay. Lacunae, I believe that's Italian. Like luck, you know, when you see those lakes in parts of Italy, something luck, you know, where who's George Clooney, he's always up there riding around on his boat. He's got a house up there and his wife and kids, right? he's got a nice chalet on one of the lakes, the lac. Okay, so lacunae means lake, or something like that. That's derived from the Italian. Okay. So anyway, lacunae, space, cavity. Of course, it's not as big as a lake, but that's kind of the derivation. And then they communicate with each other via little philopodia, which are kind of like a philopodia would be like a very skinny microvillus, okay? And these little philopodia reside in canaliculi, canal, space, cavity, right? So philopodia within canaliculi, and they connect to each other via gap junctions. Okay, you remember gap junctions from cell biology organelles 2 lecture? So they can rapidly communicate with each other, and then these gap junctions, you can get a chain of up to 20 osteocytes, okay? So they can transfer gases, right, from oxygen, carbon dioxide, and small metabolites and things like that to maintain their viability. So these osteocytes are also controlled by a couple of hormones. Parathyroid hormone, if it makes its way to these cells, it can promote reabsorption. These osteocytes promoting reabsorption of adjacent matrix. And parathyroid hormone is derived from chief cells of the parathyroid gland. And conversely, they can be caused to deposit bone via calcitonin, which antagonizes reabsorption, so basically promoting some deposition. Calcitonin is derived from parafollicular cells of the thyroid gland. And we're going to come back to those two hormones momentarily. So here's a schematic of a bit of bone. So this very pinky purple material, that's the mature bone that is saturated with the calcium phosphate. Here's our mesenchymal tissue out here. And then here are our osteoblasts that reside on the edge of the forming bone. They're depositing the osteoid, which is not yet fully mineralized. So then the osteoid always stands as a lighter area because it's got more organic material like the type 1 collagen, GAGs, and proteoglycans, and has not yet been fully mineralized. Once that osteoid becomes mineralized, it stains a darker color, and then it can trap our osteocytes residing in our lacunae. Okay, so that's what bone looks like. Compact bone contains osteocytes in lacunae, and we can see now the philopodia between adjacent canaliculi and the philopodia make a communication with adjacent cells. So you can get a chain of 20 osteocytes communicating via the philopodia from one cell to another. And eventually, of course, they'll communicate with the outside of the bone where they can pick up nutrients from blood vessels and so on. And then the fourth and most different cell type, I think, is the osteoclast. It's large, it's multinucleated, so you can usually identify it because you've got multiple nuclei. It's derived by fusion of monocytes. And it's also a non-dividing cell, and it resides in this little cavity or space here called Haship's lacuna. So you'll see it sometimes in a little indentation shown here, and sometimes you'll see a ruffled border, which is actually the cytoplasm thrown into a large number of folds, which increases the surface area for reabsorption. So that's our osteoclast. Here you can see an osteoclast here. This is the mature bone. And you can see 1, 2, 3, 4, 5, 6, 7, 8 nuclei, right? So it's large and it's multinucleated. And you can see this ruffled border. You can see kind of this, how it's folded backwards and forwards, which is increasing the surface area for reabsorption of the bone. Here you can see it in an electron micrograph. There's a bit of cytoplasm of the clast. Here's our mature bone, and here is this ruffled border of cytoplasm. It looks almost like a bunch of little microvilli, but they're not. It's a ruffled border, just folded cytoplasm, which has a large increase in surface area where they can secrete materials onto the bone for reabsorption. And there's two major mechanisms how these osteoclasts can reabsorb bone. Firstly, they can promote localized acidification. So basically, within the osteoclast you can get carbon dioxide and water formed in a chemical reaction to form a hydrogen ion and bicarbonate. So hydrogen ions, we know what hydrogen ions are, right? That is acid, okay? So you can secrete these hydrogen ions onto the matrix of the formed bone, and that will react with, for instance, the calcium phosphate to give you hydrogen phosphate and liberate free calcium. So that's kind of that's attacking the inorganic component, the calcium phosphate. And then we also have a enzymatic component to digestion, where the class may secrete collagenases and other enzymes. So collagenase, what did I say the main type of collagen is in bone? Type 1 collagen. So you want a collagenase to digest the type 1 collagen. So that makes sense. You're going to secrete collagenase and some other enzymes that will attack the glycosamic glycans and proteoglycans to digest the organic components. So now you've got those two mechanisms, the acidification to attack the inorganic calcium phosphate and the enzymes to attack the organic components of type 1 collagen, glycosamic glycans, proteoglycans. And through this mechanism then you can digest away the matrix for the remodeling of the bone, okay? And this is controlled by a couple of hormones. Parathyroid hormone indirectly stimulates the activity of the osteoclast because the parathyroid hormone actually binds to receptors on osteoblasts. And then the osteoblasts secrete growth factors that will stimulate the osteoclast activity. Okay, so it's an indirect effect. And then conversely, calcitonin will antagonize that effect. Okay, it will directly inhibit reabsorption by the osteoclasts. So then this either degradation or inhibition of that degradation facilitates the remodeling of bone. So now we can look at the organization of bone. On the periphery or in the inside there is a cellular layer called the periosteum, next to the bone. Okay, endo, inside the bone. So periosteum typically is on the outside, endosteum is on the inside of some of the bone components, and then of course we have the bone proper, which is the mineralized components of bone. So the periosteum appears thus. Basically it looks like a layer of fibroblasts perhaps. And we have a fibrous layer of periosteum. And then we have a layer of osteogenic periosteum, which is now differentiating into perhaps osteoblasts to deposit the osteoid. And this osteogenic periosteum is bound to the bone proper via Sharpey's fibers. And Sharpey's fibers are basically collagen fibers, mostly type 1 collagen fibers that are holding the osteogenic periosteum to the bone proper. And then sometimes we'll have a cavity drilled into the bone. These we call Volkmann's canals, and these contain blood vessels and endosteum that can penetrate through the bone. Endosteum is on the inner surface of the bone. So endosteum is much thinner than periosteum. Typically the osteoblasts, okay, and perhaps osteoclasts that we see attached to bone proper is what basically constitutes endosteum. It's that very single cell layer almost of cells that will line any sort of bone on the inner surface. Okay, so periosteum and endosteum, which is basically that mesenchymal tissue that can differentiate into bone-forming cells, is very important for the remodeling of bone and repairing of bone. And so what happens then, you can get the periosteal mesenchymal cells to divide, and then they can differentiate into either a cartilage pathway or a bone-forming pathway. And that commitment of the periosteal or endosteal mesenchymal cells into a bone pathway or a cartilage pathway is totally dependent upon the presence or absence of blood vessels. So you'll recall cartilage lacks blood vessels, right? Lacks blood vessels. So if you do not have any blood vessels in the area where you are remodeling bone, the mesenchymal progenitor cells will differentiate into the cartilage pathway and form chondroblasts and chondrocytes to form cartilage. If you do have blood vessels in that remodeled area of bone, those mesenchymal progenitor cells will differentiate into first osteoblasts and osteocytes, as we had previously discussed in the other two slides. So, and this is very critical for bone repair as well. It's all dependent upon the vascularity of, or in the region of the bone undergoing remodeling or repair, if it's a fracture or a break. And we'll talk about that in much greater detail in the second hour. Now, when bone is first deposited, we call it immature bone, and that's because the collagen fibers are more randomly oriented. Okay, so you see that during initial embryological deposition, and you see it during bone repair, and then that bone undergoes remodeling, whereupon the collagen fibers are layered in a more arranged orientation, and so then we call that mature bone. And that mature bone can be in the form of both spongy bone and compact bone. So compact bone is that really hard bone on the edge. So I'm sure you've all looked at a chicken bone. Maybe you've seen a cracked chicken bone, right? Or some sort of bone that's broken on the edge. It's really smooth and hard. That's the compact bone. And in the side adjacent to the marrow cavity is kind of spongy. Looks more like this. Okay, we call that cancellous or spongy bone. Cancellous bone can give rise to compact bone, but it doesn't always give rise to compact bone. It may stay as spongy or cancellous bone, and in some cases it may give rise to compact bone. So first we get the spongy bone, and we talk about trabeculae and spicules. You see these little branches here. These are called trabeculae or spicules, and so this is the true bone here. And in the center we have bone marrow. Okay. And then, so we see this spongy bone in many different locations, and we can get sometimes with bone remodeling the fusion of some of these trabeculae and spicules together. So compact bone can form from spongy bone by the fusion of some of these trabeculae. So like if this and this fuses together, we're going to trap a blood vessel like this. You can see it fusing together. You trap a blood vessel. This would be the very beginning, perhaps, of some compact bone. And then if we get compact bone, mature compact bone, we see these Haversian systems or osteons. Haversian systems are osteons. Makes up much of compact bone. At the periphery, either on the outside and the inside, we also have inner and outer circumferential lamellae. I'll come back to this. And then sometimes we have degraded fragments of these osteons or Haversian systems, which we call interstitial lamellae. We're going to come back to all this. So here's a schematic of compact bone. So at the very outside of the compact bone, we would have the periosteum because it's on the outside. And on the inside, adjacent to the bone marrow cavity, we would have the endosteum because that's on the inside. Going back to the outside, immediately below the periosteum, we will have an outer circumferential lamellae. So this would be a layer of compact bone that goes all the way around in cross-section the perimeter of the compact bone. And then beyond that, we start to get the osteons or Haversian systems as shown here. Okay, and in the center of which we'll see a blood vessel, sometimes lined with bone-forming cells. And then in between these osteons, we have remnants of old osteons, which are the interstitial lamellae. And then once we go towards the bone marrow cavity, we'll have an inner circumferential lamellae, not labeled here, then the endosteum and the marrow cavity. So we can see that again in this schematic of compact bone. We see at the periphery the periosteum. We have the outer circumferential lamellae. We have our osteons. We have some interstitial lamellae. It doesn't look like it's labeled on this one. Bits of old osteons between mature ones. And we have an inner circumferential lamellae. Then there'd be an endosteum and then the marrow cavity. Also shown in this particular slide are the Volkmann's canals. The Volkmann's canals form a zigzag type space between the cavity down the center of the osteon. So this is very important because then by zigging and zagging and zigging and zagging, you can get a blood vessel from the outside of bone all the way through this compact bone to the bone marrow cavity. Okay, so then those Volkmann's canals form the kind of the crosses of the ladder, if you like. Yes. No, it's much bigger than a canaliculi. So you can actually see the size in the schematic of the canaliculi, roughly, right, of the osteocytes. The Volkmann's canals are much bigger because they're carrying blood vessels. So they're very important for carrying nutrients into and out of the bone, and also they form a route for newly formed components of blood that's being formed in the bone marrow cavity to get out into the circulatory system. Okay, so here's another view of compact bone. Here's our periosteum. Here's the osteogenic periosteum differentiating into blasts that then deposit bone. And here's our osteons, shown here, some interstitial lamellae, and here's a bit of marrow here. Another view, here's our osteon. Okay, you can see the canal of the osteon. You can see some interstitial lamellae, remnants of old osteons. And here's a Volkmann's canal from one Haversian canal down the center of down the center of an osteon here and here, forming a bridge between two adjacent osteons. And it would zigzag, all the way across this compact bone. Okay, so how do we calcify bone? Well, initially it is done through the osteoblasts. Remember, the blasts formed by differentiation from mesenchymal cells. And the osteoblasts secrete the organic matrix, type 1 collagen, glycosaminoglycans, proteoglycans, which we then recognize as osteoid, that different stained layer between the osteoblast and the mature bone. The osteoblasts secrete a number of different factors that promote the calcification and mineralization of that newly formed osteoid. They secrete these various glycoproteins which act as calcium binding proteins. So these calcium binding proteins then in the osteoid will facilitate the precipitation of calcium phosphate into and around that forming osteoid to form mature bone. And then, of course, eventually the osteoblasts secrete so much osteoid they become surrounded and trapped by it, whereupon we recognize them as osteocytes residing in lacunae, okay? And then the osteocytes we know have limited capacity for deposition and reabsorption because they're trapped now in the compact bone. Factors that contributed to calcification. So alkaline phosphatase promotes accumulation of the inorganic phosphate in the osteoid. And of course, as you get more and more calcium phosphate, eventually it reaches a saturation point where it will precipitate out as a salt, as the calcium phosphate salt. And that's also facilitated by these calcium binding proteins that will bind that calcium phosphate and keep it in place. And this deposition of calcium phosphate inorganic material is actually antagonized by pyrophosphates that then can inhibit calcification. So you can see that here. Here's some cytoplasm. This you may recognize as type 1 collagen. Type 1 collagen has that periodicity that we talked about last week. And you can see these black blobs pointed to by the arrow, which is calcium phosphate it's reaching a saturation point where it's starting now to precipitate out of solution and being bound by the proteins, the type 1 collagen and the glycosaminoglycans and proteoglycans of this forming osteoid. Okay, so now you can see how the combination of the organic components containing some calcium binding proteins can facilitate precipitation of the inorganic component, the calcium phosphate. So bone remodeling, deposition and reabsorption is important for many different things. Turnover, like for instance, bone remodeling can ensure new blood vessels can make their way through the compact bone to sites where they're needed. Or you can reabsorb bone. You might need canaliculi or a new blood vessel or new Volkman's canal through compact bone. So reabsorption can facilitate that process of forming these canals. Also remodeling, just maintaining the growing bones and the shape of various bones. Okay, and so these are all constantly undergoing remodeling, and of course we know that this remodeling reabsorption is facilitated by parathyroid hormone, or antagonizing that effect, calcitonin will promote bone deposition. So we're having constant remodeling. It's a slow process, but constant. So here are some examples of diseases that we might see that are caused by out of kilter unbalancing of this deposition and reabsorption process. So osteoporosis, I think you probably have all heard of that term before. Women, when they become menopausal, sometimes they become osteoporotic. In this case, reabsorption is greater than bone deposition. So here's normal bone, and here's a piece of bone that is from an osteoporosis patient. So you can see how much thinner the spongy bone is and the spicules are. So it would crack a lot easier, and that's of course an issue with women that have osteoporosis. Their bones break easier. So conversely to bone reabsorption, you can have deposition greater than reabsorption. So this is an example. There's osteoporosis, where you have an excess of bone deposited. Sometimes this is called marble bone disease, and quite literally it's sometimes called stone bone disease. You can see how thick the compact bone is of this piece of skull with this person with osteopetrosis. So some of the factors that control, nutritional factors that control bone deposition and reabsorption shown here. So vitamin C, why would vitamin C be important for bone deposition? Because we know vitamin C is required for collagen synthesis, right? And we know type 1 collagen is a major component of bone. Yes? Muscle will turn into bone. Maybe it's excess calcification, which could result from deposition exceeding reabsorption. So, for instance, if you had a downregulation of parathyroid hormone, so you're not getting reabsorption, you might get excess deposition. If that's what you're talking about, but it's probably several different ways to get that. So vitamin C, collagen synthesis required for type 1 collagen in bone. Vitamin D plays an important role in the uptake of calcium from the GI tract. Okay, so you need vitamin D for the normal formation of bone because you need the calcium taken up. So if you didn't have, if you had a vitamin D deficiency, which sometimes occurs, you could have weak bones, okay, breakage and so on. Vitamin A has a somewhat more complex effect. Deficiency plays a role in fetal and skeletal formation, and in excess it can actually cause acceleration of the conversion of cartilage into bone during growth, which we're going to talk about in the next lecture. Here's some hormonal factors. So growth hormone is very important for the growth of bones. So if you have a deficiency in childhood, this could lead to dwarfism. Okay, there's multiple causes of dwarfism. One of them would be here. If you have an excess of growth hormone in childhood, you could have giantism, as your name implies, the child will be very tall. Or as an adult, if you have growth hormone, excess of growth hormone in an adult, which quite often is caused by a tumor of the pituitary gland, because that's where growth hormone is synthesized and secreted, this can lead to acromegaly, which is an enlargement of the skeleton. Sex steroids play an important role in bone formation. So because they influence the timing of the ossification of long bones, the conversion or the cessation of elongation of long bones. the closure basically of the epiphyseal growth plates. So for instance, if you have precocious puberty, so if you undergo sexual maturity at an early age, that will tend to stop growth, so you'll be a shorter person. If you have delayed puberty, and this can be caused by a number of things, for instance, kids that are exercise a lot, extreme athletes, okay, they're running marathons, triathlons, running all the time, those kids tend to be tall. And guess what? When you see those, when you look at these long distance runners, they're always skinny and tall, right? They're always skinny and tall, right? So who knows whether that happened as a child, but you know that what happens is if they're exercising extremely, they have a delayed puberty, they grow taller, which works out well if you're a long distance runner, and that's what happens with delayed puberty. And then you can also have hyperparathyroidism, which is excess parathyroid hormone, right? So that's going to reabsorb bone, so the bones are going to be very fragile and break a lot. Okay, here's an example of acromegaly. Here's an enlargement. This is an enlargement of the skeleton caused by a pituitary tumor. Too much growth hormone in the adult, not in the kid, but in the adult. And you can see the size of the skull of this person that had acromegaly as opposed to presumably the normal size adult. You actually see these people in a lot of movies, right? You see them in some of the James Bond movies where you've got this really huge guy who's beaten up on James Bond, right? There's one of them that had like metal teeth in his jaws. I forget which movie that was. But that guy had acromegaly. You see it occasionally in these movies where they're huge, right? They're really huge, and they've probably had acromegaly, and then of course they can be typecast for those types of people in certain movies. Yes? Not sure. Depends. If it's acromegaly, it would have been a pituitary tumor as an adult. Not sure when the tumor started to grow. It's possible it started to grow earlier, and so he might have been tall. But in this case, you know, it's as an adult. You know, you could probably have a range. Okay, so there we go for the first hour's lecture. So here's our question. Practice question. Which of the following is not a mineralized component of bone? Not a mineralized, being the operative word, component of bone. So, is the Haversian system mineralized? How about the outer circumferential lamellae, the endosteum, the interstitial lamellae, or the inner circumferential lamellae? Do you think you know the answer? Okay, endosteum is, remember, that's those mesenchymal fibroblastic-like cells. Okay, let's take a break for 5 minutes, if that's okay, and then 20 minutes on the hour, we will move on. Okay, so now we know the cellular and acellular components of bone and how it's organized, the architecture, some of the hormones and growth factors that control the remodeling of bone. Now let's look at somewhere the let's see here. The remodeling of bone development. There we go. Very good. Bone development. Okay. Bone development. So the objectives for this lecture: know the mechanisms of bone ossification and some of the many of the steps that occur during bone development from fetal formation until we stop growing as an adult, and know the mechanisms between endochondral ossification leading to bone elongation, how that occurs until it stops. Then we'll talk about how bone repair occurs after a break. And then we're going to talk about joints, okay, so the tissues around articulating bones. Okay, so I just want to briefly mention the evolution of bone, which actually is important for the bone repair aspect. So if you look at the phylogeny of bone development in the vertebrates, obviously prior to vertebrate evolution, we have invertebrates coming along first, and they didn't have any hard structures in many of them, so you don't get many fossils in the Precambrian, so fossils are rare. In the Cambrian and thereon, we had vertebrate skeletal structures, and so we have nice skeletons, and we can follow that. So what happens is the evolution of bony structures in the vertebrates starts out with our amorphous and fibrous components, where we didn't have skeletal structures. Then with the right combination of those amorphous components, we can get cartilage, which is somewhat more rigid, so then we get skeletons, and then that cartilage can be calcified. So there's a sequence of the amorphous and fibrous components. Then in higher vertebrates, like cartilaginous fish, we had cartilage formed, and then the cartilage become calcified to form bone. That sequence we will see in embryological development of bone, and we will see that same sequence in bone repair. And they're all three are interrelated, so it makes a lot of sense in terms of how these things came to be the way they are. So for this lecture, we're going to talk about, I'll give a brief introduction, and then there's two main mechanisms of ossification, intramembranous and endochondral. We talked quite a bit about intramembranous ossification, which is the name given to the mesenchymal cells becoming osteoblasts, osteocytes. Endochondral is basically cartilage replacement, and that occurs in restricted regions where we don't have a perichondrium. Then we'll talk about bone repair, joints, and a few clinical examples for relevance. So you may remember, in terms of bone growth, we start out with a mesenchymal progenitor cell. It can be either the periosteum on the outside or the endosteum on the inside, and depending upon the presence or absence of vascularity, i.e. oxygen, then those mesenchymal cells can either differentiate into, in the absence of blood vessels and oxygen, they will become cartilage. Okay, they'll become chondroblasts and chondrocytes, which then can form cartilage through appositional and interstitial growth, which hopefully you kind of remember from last week. Or if we have blood vessels and oxygen, that will cause those mesenchymal cells to differentiate down the pathway towards bone, forming osteoblasts and osteocytes, osteocytes that then can form bone through both an intramembranous and endochondral mechanism. So it's really the presence or absence of the oxygen and the blood vessels that shifts the mesenchymal cells into a cartilage pathway or a bone pathway. And that's very important when it comes to bone repair. Okay, so here's our two mechanisms again, intramembranous and endochondral ossification. So intramembranous ossification is more of a direct mechanism where our mesenchymal cells in the periosteum on the outside and endosteum on the inside can then be induced in the presence of a vascular environment to differentiate into the osteoblasts that secrete the osteoid, become trapped in the osteoid, become osteocytes. Okay, so it's a differentiation of mesenchymal cells into osteoblasts and osteocytes. That's the most common mechanism. Much more restricted is endochondral ossification. And endochondral ossification, you can simply consider it as cartilage replacement. You have a pre-existing piece of cartilage, it is reabsorbed and replaced with bone. And that occurs in those locations where we don't have perichondrium, such as articulating surfaces, the epiphyseal growth plate, places like that. So let's first talk about the most common mechanism, the intramembranous ossification. Okay, it occurs in most locations of the body where we have vasculature flat bones, some shorter bones, bone collar and so on. And as I mentioned, involves the differentiation of our mesenchymal precursor cells into osteoblasts, which secrete osteoid and eventually become osteocytes. So here we can see a schematic of this intramembranous ossification. Here's our mesenchymal cells, and they're being induced to differentiate into osteoblasts. Now sometimes you'll see the term bone blastema. Bone blastema refers to these plump cells that look like osteoblasts that have not yet attached to the bone, but they look like an osteoblast. So they're differentiated into an osteoblast, but they haven't secreted enough of the osteoid to show what would appear to be a normal piece of bone. These bone blastema osteoblasts then may appear thus next to a piece of bone where they are secreting the osteoid, shown here. Okay, so intramembranous ossification, pretty straightforward. Mesenchymal cells differentiate into osteoblasts, which secrete the osteoid and then become osteocytes. So you can see that here in this spongy bone. You can see these mesenchymal cells in the endosteum in this case, secreting, turning into osteoblasts and then secreting osteoid, becoming components of bone. Now, yes? Yes, this clear layer right here is the osteoid. The osteoid is always immediately beneath the osteoblasts. And when we look at a bunch of examples in the lab, and maybe a few slides momentarily, you'll see it always stains lighter. Depending upon the slide, it always stains differently. Okay, so now sometimes spongy bone can become compact bone. And this occurs by the spongy bone spicules and trabeculae fusing and trapping a blood vessel. And then you can get a circumferential deposition of more bone by the osteoblasts on the inner aspect, forming the circumferential lamellae. So then there's one ring here, two rings here, three rings, and so on. So eventually it kind of fills in. So this large, what was a large space, becomes now a much smaller space with these concentric rings, lamellae, forming what we recognize now as a Haversian system, an osteon. Okay, so it's just by filling in a larger space, always around a blood vessel. Okay, so endochondral ossification is the other mechanism, which is much more restricted. Endochondral ossification, simply think of it as cartilage replacement. So endochondral ossification is very important during fetal development and during elongation of bones from postpartum until you reach your adult stature. So in the prenatal aspect, initially we get a hyaline cartilage model. We get a template, right? Sometimes called an Anlagen, which is German. Anyone speak German? No one speaks German. Anlagen is German. It's an embryological German term, meaning template, precursor, thing like that. You see it sometimes in embryology. So we've got this template that's formed from hyaline cartilage, okay? And then around this, let's say it's a long bone that's forming. We've got a template of a long bone now. It starts out as a piece of cartilage. And then around that piece of cartilage, we have intramembranous bone formation. Intramembranous as in mesenchymal cells differentiating into osteoblasts, okay, depositing osteoid, forming bone. So you get this collar around the cartilage. So you've got cartilage in the middle and the collar around the outside of bone. And then that cartilage in the middle that was the template is replaced via an endochondral mechanism. You get cartilage replacement. You get reabsorption of that cartilage and replacement with bone via an intramembranous mechanism. That happens in the fetus, okay, to form the shape of the bones, the long bones and other bones. Then during postnatal growth, we have an epiphyseal growth plate, which, for instance, in long bones is a piece of cartilage between the diaphysis, the long bone, and the epiphysis, the capping round piece, okay? And that epiphyseal growth plate is important for elongation of long bones, and we'll talk about that momentarily. So let's go back and look at this in detail. So we're back in the fetus now, and here's our long bone being formed as a cartilage template, okay? Here's that cartilage template, shown here, cartilage template. And then around that cartilage template, we have a collar formed via an intramembranous ossification mechanism, bone collar, intramembranous, okay? Intramembranous as in mesenchymal cells differentiating on the osteoblast secreting osteoid becoming bone. So we're still here in the red box. So we've had a template of cartilage. Cartilage came first, then we have a collar formed around the cartilage. Then what happens is we have endochondral ossification. So the cartilage that is trapped now with the bone collar is invaded by blood vessel or vessels, and then we start to get cartilage replacement. So that cartilage that's in the center, surrounded by that bone collar, is eroded and it is slowly replaced by bone. So that's what we call endochondral ossification, basically cartilage replacement. This is still going on in the fetus, okay? So here we see this again. Here's our cartilage template. Here we see the bone being formed by an intramembranous mechanism. So the intramembranous formation is actually more responsible for increasing the width of the bone, because you're getting this collar formed around the perimeter and it gets thicker and thicker, so we're increasing the thickness of the bone. Then we get invasion of the cartilage template with blood vessels, and then that facilitates the replacement of the cartilage with more mature bone. So that would be the endochondral cartilage replacement with bone. And that endochondral ossification is important for elongation of bone, for growth in stature. So then that occurs from birth until you reach your adult height. And when that happens, so here's our diaphysis, di, two ends, epiphysis, the knob on the top, shown here. We start to get what is called a secondary ossification. So this knob shown here of the forming long bone becomes invaded with blood vessels in the center, undergoes endochondral ossification. So now we've got this secondary center, because we had the primary here in the diaphysis. Now the epiphysis is starting to be ossified through endochondral mechanism. So we've got a secondary ossification center. So between the secondary ossification and the primary of the diaphysis, we have a layer of cartilage which becomes the epiphyseal growth plate, as shown here. And this epiphyseal growth plate remains and plays a role in elongation of bone up until you reach your adult stature. So you can see pictures of that here. Here's our diaphysis, and here is what will become the epiphysis, but it's still cartilage here and cartilage here. And then in this particular case, if you get a blood vessel going into the epiphysis and you start to get endochondral ossification, you'll get the secondary ossification center, as shown there. And you can get different combinations of primary, secondary, sometimes you can even get a tertiary ossification center in various types of bones. So now we're in the teenage years, where we're getting elongation of the bone because the epiphyseal growth plate plays a role in elongation of bone, and I'll show you how that occurs momentarily. Once you reach your adult stature, the amount of growth hormone being secreted from the pituitary declines, because the growth hormone is important for the growth of the epiphyseal growth plate. I'll talk about that momentarily. Once you reach your adult stature, the growth hormone is reduced in titer, so the cells of the epiphyseal growth plate are no longer being replaced with bone, so then the bone stops growing in stature. And when that happens, the diaphysis and the epiphysis fuse, and there's no longer cartilage there. So at that point, you are no longer going to increase in height. That is your final adult height. And this is actually can be used in forensic pathology sometimes if they're trying to get, they find some bones in the woods or whatever. Do you guys remember, was it Sandra Levy? Sandra Levy? No, she was an intern. Sandra Levy, was it Sandra? Yeah, she was an intern that worked on the Hill here in DC for a congressman from California. She disappeared. They thought the congressman was responsible. Then they found this other guy that they linked to her. And then a year later, they found some bones in Rock Creek Park, right in DC. They thought maybe this is her bones because all the flesh was gone at that point. So they get the bones, and then what they can do is they can x-ray the bones and look for the presence of the epiphyseal growth plate. So if there's no epiphyseal growth plate, that means this person is an adult. You could have had a tall kid, right? That might have been 15 that was tall. If they x-rayed bones and found an epiphyseal growth plate, then they say, okay, this is a teenager, not an adult. So depending upon the degree of closure of the epiphyseal growth plate, forensic pathologists can give a rough idea as to the age of a particular individual. Okay, so here's how the epiphyseal growth plate plays a role in elongation of bone. So here's our diaphysis containing spongy bone. Here's our epiphysis, the secondary ossification center. And in the middle, between the two, is a cartilage plate called the epiphyseal growth plate. And the epiphyseal growth plate contains a number of regions: a resting zone, mitotic zone, hypoplastic zone, ossification centers, and so on. The mitotic zone, the proliferating zone, is where the osteoblasts are proliferating in response to growth hormone from the pituitary makes its way to the liver, where it causes secretion of somatomedins, which is like an insulin-like growth factor 1, through the circulation, makes its way to the proliferation zone, causes the cells to proliferate. So, through a number of steps, growth hormone is causing proliferation of the chondroblasts in the epiphyseal growth plate. So what happens is these cells proliferate and they increase the thickness of the epiphyseal growth plate, pushing up the thickness, pushing up the height of the long bone. At the same time that this region of the proliferating zone increases in thickness, the same thickness on the trailing edge of the epiphyseal growth plate is converted into bone. So it's kind of like the epiphyseal growth plate ratchets up. It increases in thickness, but then that increase in thickness, the same thickness on the trailing edge, is converted into bone. So the growth plate is growing up. It's never getting thicker. It's widening, but at the same time that it widens, the same thickness is removed from the trailing edge and converted into bone. So it kind of ratchets up. So that's how an epiphyseal growth plate, as shown in this example, is responsible for increasing the length of the bone. Okay? And this shows you a nice light microscopic view of the epiphyseal growth plate. Here's our resting chondrocytes. Here's our proliferating chondroblasts that are responding to growth hormone to increase in mitotic activity. Then, as you go towards the trailing edge, some of these chondroblasts become hypertrophic. They increase in size. They actually rupture, and you get calcium salts penetrating into this trailing edge of the epiphyseal growth plate, converting some of those cells into calcified areas of the epiphyseal growth plate and allowing bone-forming cells to migrate into that trailing edge and start to deposit osteoid and whatnot to form spongy bone on the trailing edge shown here. Here's another view of the same thing. This is the diaphysis, this is the epiphysis. Here's our epiphyseal growth plate, these different zones: resting zone, proliferating zone, hypertrophic zone, zone of degeneration and calcification. So sometimes things can go wrong with the epiphyseal growth plate. So here's a disease, Blount's disease, thought to be due to uneven weight on the epiphyseal growth plate. So this then causes growth to be uneven, and this individual then has this bow-legged type of appearance because of uneven weight on the epiphyseal growth plate, uneven elongation of the long bone. Okay, bone repair. So bone repair, who's ever had a broken bone? Okay, now we're getting some examples. Broken bones, right? So I'm sure that was painful. You remember a lot about it. For the most part, if you've had a major broken bone, the repair occurs by endochondral ossification. What do I mean by endochondral ossification? Cartilage replacement. Okay? So what happens when you break a bone? First thing is you interrupt the blood supply. Okay? You've broken the bone. You've probably broken some blood vessels around that bone. And what do we know when we interrupt blood supply? Oxygen content goes down. So the mesenchymal cells on the edge of that broken bone, there's no longer oxygen supply because we've got disrupted and broken blood vessels. So those mesenchymal cells are going to go which way? Towards cartilage or towards bone? Cartilage, because there's no longer an oxygen supply, right? So that means as you start to get the repair of this broken bone, it's going to be in the cartilage pathway because there's an absence of oxygen and blood supply. So that means initially those mesenchymal cells at the edge of the broken bone are going to do a cartilage repair, and you'll get chondrocytes and chondroblasts, mostly chondrocytes, formed from the mesenchymal progenitor cells. So this cartilage will form a bridge, a temporary bridge, connecting the two bits of broken bone together. It's a cartilage bridge, right? So eventually you've got a nice cartilage bridge. It holds the two bits of broken bone together. Usually, you put a cast around it because you don't want it flopping around. You want it to be sort of stable so that the cartilage can form a very secure bridge between the two bits of broken bone. And that can take at least 4 days, okay? After you've broken a bone, it can take at least 4 days for the initial formation of the cartilage bridge. Once that happens, once you've got cartilage bridge formed, eventually you're going to get some blood vessels that can penetrate back in with tissue repair into and around that cartilage, okay? And once you get those blood vessels penetrating into and around the cartilage, we will get endochondral ossification. Endochondral meaning cartilage replacement, okay? Initially cartilage, then you're going to get bone. And this makes sense in terms of what I told you about the evolution of bone and the embryological development of bone. First you have the biochemical components, right? Fibrous and amorphous components. Then you have cartilage during evolution and during embryological development. Remember, the cartilage is the template, is the first component that's laid down, a cartilage template, and then it's replaced by bone, right? So there's that sequence. All three of those events, the evolution of skeletal structures, the embryological development of skeletal structures, and now we see in bone repair the same sequence. They're all interrelated, and I think we can see now, because of the way those three things are interrelated, it makes sense that for the most part bone repair is going to be an endochondral mechanism. And then once we start to get ossification of the cartilage, that can take at least 2 weeks before we start to get bone deposition. Okay, so it takes a while. At least 2 weeks, as early as 2 weeks. It may take longer depending upon how severe the fracture was, okay, and if it's stable, right? Okay, nice cast, and you're not wobbling it around too much. So it takes at least 2 weeks for the beginning of bone repair. Okay, this shows you this schematically. So we've broken our bone. The periosteum and endosteum, in the absence of a vascularity, will form a cartilage bridge, which then appears thus. And then after a while, once that cartilage bridge forms a stable link between two bits of broken bone, we can get some blood vessels penetrating into that cartilage bridge. We get endochondral replacement of the cartilage with mature bone, and of course it remodels. Initially that's a primary bone, which is immature unwoven collagen fibers. Then it's replaced through the turnover mechanisms that we talked about, and eventually we get something hopefully that appears like this, where we've got a nice healed fractured bone. Okay, so you can have different severities of fractured bone. Okay, You might say this guy's all screwed up, right? When he had his, whatever it was happened to him, he certainly had something severe. Who knows how long those things are going to be? And he's got a plate, screws, the whole thing. Here's a very mild, this is about the mildest break you can get, this compression fracture. This is actually from my daughter when she was 6 years old. She jumped off a swing and landed hands down like this. And she said it hurt. We were going to the beach a couple of days later. She said, no, it hurts. It's like, no, it's okay. It's not broken. So after 3 days, she said, still hurts. It's okay. We took her to the hospital, and they took an x-ray and said, yeah, she's got a compression fracture. So they put a cast on her hand. So basically, she's just kind of cracked it across here. See this line here? And the orthopedist said, yeah, a lot of times people don't even know that they've got a compression fracture, and they just deal with, apparently, a lot of farm kids. You know, they're always injuring themselves on the farm. So a lot of farm kids, they never get anything done. It just repairs itself. Okay, so you go from one extreme to another. She had a cast on her hand, though. Okay, so the next thing I want to talk about are joints, movable joints, right? Articulating joints. So there's joints come in two major varieties. Okay, the synarthroses, these permit little or no movement. I'm not going to talk much about synarthroses. They're not particularly important. Here's an example of a synarthrosis where the bones of the skull fuse together. Okay, so this is a non-moving joint where different bones of the skull have fused together. What I do want to talk about are the diarthroses, which are movable joints, elbows, knees. And these joints are capped. Is that a cricket? He must have liked this topic. So we have articular joints which have the bones capped with cartilage, and they have no perichondrium, right? No perichondrium, which is very important. And then within that joint we have fluid as a lubricant, and we have a connective tissue capsule at the perimeter, which holds the joints together, and we have a fibrous membrane and an inner synovial membrane containing A cells and B cells. The A cells immediately adjacent to the synovial fluid are phagocytic, because if there's any debris that's in there, they want to get rid of it. And beneath the A cells are cells that secrete the synovial fluid, the B cells. And these can be reinforced with ligaments and tendons and so on. So here's a schematic of our articular joint. The blue is the space, the articular cavity. Here's and it's surrounded by a synovial membrane, and the white is the cartilage, okay, the articular cartilage. Now, the articular cartilage does not contain perichondrium. You can imagine if you had a perichondrium, when you've got two articulating surfaces, the perichondrium can rub off, so you don't have a perichondrium in articular cartilage. Is shown here, no articular cartilage. Here's our long bone. Here's a section through the cartilage. And the interesting thing about articular joints is that the collagen, which would be type 2, because we're talking about cartilage, the type 2 collagen in the articular cartilage is kind of curled over in this arch, which is actually makes a lot of sense, because if they're arched, when two pieces of cartilage, articular cartilage, rub against each other, they're going to kind of roll off each other. If the cartilage was kind of sticking straight out and you had two articular surfaces rubbing against each other, you could imagine that the little bits and pieces of cartilage would rub right off the end, right? So you'd get the articular cavity filled with debris and bits of collagen. So by having the type 2 collagen in this arched arrangement, they're going to slide over each other and limit the degree of debris formation in the cavity, the articular cavity. So here is the membrane at the periphery. Remember the A cell, this is the synovial fluid and the space here. The type A cells are phagocytic to phagocytose any debris. The B cells are actually secreting some of that fluid to promote lubrication between adjacent articular surfaces. Okay, and then we can have attachment to the cartilage or bone, we can have a tendon where we have muscle attached to bone, or a ligament bone to bone, usually through Sharpie's fibers, that type 1 collagen fibers. And then sometimes in these joints we have rheumatoid arthritis. So, and that's in distinction with osteoarthritis. So rheumatoid arthritis is an autoimmune disease, okay, where you have inflammation of the joints. So you can see this person's knuckles. The joints of the hand here are highly inflamed and swollen because what's happened is we've had an inflammatory response. Remember the inflammation caused by mast cells and lymphocytes, what sort of mast cells and basophils. Yes, thank you. Basophils, secreting those factors that promote inflammation. So you get, with inflammation, you get fluid flowing into and around the site of inflammation. And remember, we have eosinophil chemotactic factor as part of the inflammatory response. So you've got cells migrating into the inflammatory response. So you see all these cells here. A lot of these would be, cells, eosinophils, maybe some macrophages that are in there to phagocytose. So you get fluid swelling and also cellular invasion into the site of inflammation that causes swelling of the joints, right? So you can see this inflammation here, and you can also see the swelling here. So that is rheumatoid arthritis. And of course, what people take for rheumatoid arthritis are NSAIDs, non-steroidal anti-inflammatory drugs, ibuprofen, aspirin, Celebrex, stuff like that, which will reduce the inflammation. Okay, so it's an inflammatory response, which is totally different to osteoarthritis. Remember, we talked about, I think, osteoarthritis in the cartilage lecture, where you can have bits of the cartilage breaking off the articulating surfaces. Remember, I talked about professional athletes, they get their joints scoped out sometimes because they've got little chunks of cartilage broken off in there, and the cartilage is removed. So that may lead to osteoarthritis because they've lost cartilage, maybe through some natural mechanism, sometimes through, sports injuries, things like that. That would be, and a lot of those athletes, you see them in their middle age, they're walking around with crutches because they're crippled, because they've got osteoarthritis. That's totally different to rheumatoid arthritis, which is caused by inflammation of the joints, okay? Same kind of effect, hard to walk, hard to move your joints, but the mechanism is totally different. One's inflammation, the other is damage to the cartilage. Okay, that went quickly. Here's our question, practice question. Which one of the following occurs when blood vessels reappear during repair of a broken long bone? So remember, we talked about what happens when you have a broken long bone, okay? And hint, remember, it's endochondral ossification. So, is there an increase, and that's when blood vessels reappear. Is it increase in chondrogenic potential? No, because that occurs before that. Increase necrosis? No. Intramembranous ossification? No. Increase in osteogenic potential? Yes. Periosteum becomes chondrogenic. Okay? So just think about that one. Think about the sequence of things that happen when you break a bone. Okay, so let's take another 5-minute break, and on the hour we shall do the lab. Is that okay? We do the lab and then we're done for today? Okay, very good. Okay, so let's do the lab session and we will be done for the day. So now let's look at some examples of some of the structures that we've talked about in the last 2 lectures. So here's a section through a long bone. Here's the diaphysis. So this would be filled with bone marrow and a little bit of spongy bone. and you can really make out the compact bone on the periphery. Now sometimes you see this term metaphysis. That's basically the widening of the diaphysis. Here's the epiphyseal growth plate. See this area here? This is the cartilage epiphyseal growth plate being replaced with bone via an endochondral mechanism on the trailing edge. And then on the top here is the epiphysis, and on the surface of the epiphysis will be the articular cartilage. And then because this is the epiphysis, we'd say this is a secondary ossification center. So of course the diaphysis is the primary ossification center. Any questions on this one? Yes?
So we're looking at teenager?
Yes, probably, because you can see an epiphyseal growth plate. Yes. Other questions? Okay. So then if we look at the epiphyseal growth plate in more detail, so this is all cartilage, this is the bone being formed on the trailing edge. So here's our resting zone, zone of proliferation, which is the zone responsive to growth hormone from the pituitary, making its way to the liver, forming somatomedins, one of which is IGF-1, makes its way through the vasculature to this location, causes mitosis of the chondroblasts. Long pathway, but these are the mitotic cells. Then these cells undergo maturation and hypertrophy increasing in size, and then eventually they rupture, and you can get calcium salts penetrating into this hypertrophic zone, and then they degenerate and become ossified. Okay? This is just a big plug. This would be more fetal, where we've got a large area of cartilage. Questions? Okay, so this shows you very nicely this ossification. So the blue is the epiphyseal growth plate, which is cartilage. The pink is the trailing edge of bone marrow. So here's M for marrow, a little bit of cartilage and bone. And this is stained to show you the calcium salts are diffusing into the trailing edge of the cartilage plate. Okay, so you can see how then on the trailing edge of the epiphyseal growth plate, calcium can make its way from the diaphyseal cavity, the marrow cavity, into the trailing edge, where it can gradually calcify the cartilage. Any questions? And this is shown again, same concept. The black is this von Casse stain, which stains calcium phosphate. You can see how you can see the slow, gradual calcification on the trailing edge of the epiphyseal growth plate. So this trailing edge, then the cartilage is reabsorbed, and then it will be replaced with bone-forming cells. Any questions? Okay, so now let's look at bone formation and intramembranous mechanism. So why is this intramembranous as opposed to endochondral? Well, it's intramembranous because we have a periosteum, right, of mesenchymal cells. Here's our periosteum. And then if you look here, see these cells, see how they've all got plump, they're kind of fat? That would be a bone blastema. These are the forming osteoblasts that are fattened up in preparation for attachment to the bone proper, where they will secrete the osteoid. Any questions? Here's a higher power view of the same thing. So it's got to be intramembranous because here's a periosteum, and we can make out now, we can see actually osteocytes that are trapped within the bone proper, within the spongy bone. Okay? Questions? Higher power more. So here's our mesenchymal tissue out here, which can differentiate into our osteoblasts. Now you can see this nice lighter stained area of osteoid, right, more organic, not so much inorganic material secreted by the osteoblasts. The osteoid becomes mineralized with calcium phosphate, so now it stains darker. And it traps the osteocytes in their lacunae within the mature bone. Questions? Okay, higher power view. Mesenchymal tissues out here, osteoblasts here, osteoid, lighter stained layer right here. Questions? Another view of the same thing, different stain, but you can see the osteoblasts, osteocytes trapped within mature bone. Okay. This out here, we would call this what? Periosteum, right? Peri next to the bone. Peri next to osteum, osto, bone. Periosteum. This is the mature bone. Then you can see these layers of cells immediately adjacent to the mature bone. These would be the osteoblasts, and this lighter stained area would be the endosteum, right? And inside the mature bone, we would see osteocytes that have been trapped within the bone. Any questions? Yes. Yes. The circles here are blood vessels. This is a blood vessel. This is a blood vessel. We haven't done cardiovascular yet, but yes, it is blood vessels. Yes. It can be on the periphery of compact. It can be anywhere. It is going to be on the periphery of compact bone and spongy bone. It may appear differently. It may be much thinner in compact bone because compact bone's formed pretty well. Other questions? Yes. Up here, that's the periosteum. Periosteum next to the bone, right? Peri next to osteum, bone. Periosteum. So endosteum would be this stuff on the inner surface. Endosteum is much thinner. So endosteum is going to be on the inner surface of spongy bone and perhaps next to the bone marrow cavity. And it's much thinner. It may just be one layer thick, being the osteoblasts. Okay, questions? Okay, here we can see now, look at this guy, multinucleated cell. Okay, if it's multinucleated, that means it is an osteoclast formed by fusion of monocytes, right? Multinucleated, that's a dead giveaway. So here's one here, this is maybe half a dozen or more nuclei. Here's another one, I can see at least 4 nuclei on that one, okay? If you look carefully, you can see these osteoclasts. Any questions? Here are some really nice osteoclasts, 1, 2, 3, 4. You can see the multinuclei. And now these guys reside in a Hauschilp's lacunae. Hauschilp's lacunae basically being the indentation where they're chewing away on the mature bone. So the blue is the mature calcified bone, and you can see this ruffled border here of the osteoclast, and you can see this indentation of the Hauschilp's lacunae. And the arrows are pointing to the ruffled border of the clast chewing away at the mature bone. Any questions? Okay, in compact bone, of course, we have our osteons, okay, with the central canal down the middle, and sometimes we can see a Volkmann's canal between 2 adjacent osteons. Okay, here's the Volkmann's canal forming the rung on the ladder if you zigzag all the way across through the compact bone. Any questions? Okay, here we have some more osteons, much more mature osteons. Here's our canal osteon or Haversian system, whatever you want to call it, same thing, Haversian canal. And here we have these interstitial lamellae. So this is an old osteon, an old Haversian canal that has been, an old Haversian system that has been partially digested, and this is a piece of the Haversian system that's left over. So here's another one. This looks like half of a Haversian system here and bits and pieces here. So clearly this compact bone's been undergoing remodeling where some of the osteons have been partially degraded and bits and pieces have been left behind that we recognize as interstitial lamellae. Questions? Yes? Yes, this whole thing is an osteon. Osteon or Haversian system, those two names are synonymous. Okay? Osteon, Haversian system, same thing. And then so this central Haversian canal would contain blood vessels. It probably contains some osteoblasts, okay, and maybe some mesenchymal cells. So then this would be lined by endosteum, okay? There'd be endosteum lining this Haversian canal. Questions? Okay, more compact bone now. We can see osteocytes. Remember, sites reside in a lacuna or a space, and they give off these filopodia that reside in canaliculi. And two adjacent filopodia will communicate with each other. You can have a string of up to 20 osteocytes communicating with each other via gap junctions. Questions? Okay, now we're looking on the inner surface of a long bone. So this is the marrow cavity here. Here's our Haversian system, Haversian canal, and this would be the inner circumferential lamellae that runs all the way around the bone marrow cavity. Any questions? Okay, so now we're on the outside of a piece of bone. Here's a bit of skeletal muscle. Fibrous periosteum, osteogenic periosteum. See how these cells look a little more plump? You could almost imagine they're forming a bone blastema, because then they're going to attach to this mature bone here. Okay. Then on the inner surface, this is the marrow cavity, and these cells, of course, would be osteoblasts, and we can actually make out some endosteum. Okay, this is mature bone here. Any questions? Okay, here's this is called an odontoclast, which is basically an osteoclast. Odonto from teeth, clast. So it's basically an osteoclast of teeth. Why is this an osteoclast? Because we can count more than one nuclei. I can count 1, 2, 3, 4 osteoclasts, or 4 nuclei of this osteoclast. And we can see the ruffled border where the cytoplasm has thrown into these folds, which is an adaptation to increase surface area for the reabsorption of the bone or the tooth in this case. Okay, so again, structure of an osteoclast. Any questions on this one? Okay, so now we can see a scanning electron micrograph of these. This was the hole left when an osteocyte was pulled out of this bit of bone. So you can see these little holes here. These would be the canaliculi, right? The canaliculi that held the filopodia of the osteocyte. Questions? This is a low power view of the same sort of thing. Okay, we can see some spongy bone. We can see areas where there's bone deposition, marrow cavity, and this is where we had some Haschip's lacunae chewing up some bone via an osteoclast, presumably. Any questions? Okay, now if we look at joints, here's two articulating surfaces. Okay, look in finger joints. So this is one cartilaginous surface. This is another cartilaginous surface. Remember, so these are articular cartilage. Articular cartilage. Right? So because it's articular, there's no perichondrium. So because there's no perichondrium, that means this cartilage had to form by interstitial mitosis. Remember, interstitial mitosis for the cartilage lecture. So here's our synovial space. Here's a capsule at the periphery. Here's our synovial membrane, shown here. Questions on this one? Okay, and then that membrane, synovial membrane, sometimes called a synovium, remember contains two layers of cells. The A layer of cells immediately adjacent to the joint cavity are phagocytic to take up any debris, and immediately the A cells will be the B cells, which are secreting the synovial fluid to act as a lubricant in the joint cavity so that hopefully the chunks of cartilage aren't rubbing too hard together. Any questions on this one? Okay, that went quickly. Okay, choose the correct response regarding the circled cell. Okay, so first, this is not necessarily a straight identification. First, you have to know what the cell type is. So, know what the cell type is. Is this an osteoblast? No. Does it secrete calcitonin? Mm-mm. Is it terminally differentiated? Maybe. Is it connected by desmosomes? No, it's gap junctions. Remember, the Filopodia are gap junction connected. And is it derived from osteoclasts? No, it's derived from osteoblasts. Right, so the answer then is C, terminally differentiated. Okay, there you go. We're done for today. And then on Wednesday, we're going to be looking at the components of the blood, hematology, and hematopoiesis, how those components are formed in the bone marrow cavity. Okay?